workshop today. And so I'd like to first thank you, Snakes and Lisa, for this opportunity. As everybody comes in, we should have good Wi-Fi, except for Cindy. We should have plenty of power as well, and get comfortable. There should be a break this morning at about 10:30 or so. There'll be coffee around the corner. Restrooms are also around the corner for your convenience. If you need to get up at any time, feel free to do so. Any other logistical issues? As far as I know, they're not really going to kick us out until we're ready to leave. And the way I like to work this is, okay, if they kick us out, then we'll reconvene at the bar or someplace and continue whatever conversations that you guys feel is necessary to continue. And also, I'll be around all week. I got suckered into doing booth duty at the exhibitor hall, so I'll see you there. And also, I'm doing a admittedly short Guru is in session on the Guru is in session day. I believe it's Thursday out here as well. We're splitting the time with Scott Davenport, who's a LDOM's virtualization expert, and myself doing a Guru's in session. But I'll be around all week. I actually live near San Diego, so I live about 30 miles from here. I have a ranch up in the mountains, and so this is sort of like my backyard, as the case may be. So the format today is going to be fairly free and open, and nothing in particular detail, and we'll do that. So what I'd like to do first then is I'd like to go around the room and let's just introduce ourselves. Your name, where you're from, who you work for, if you don't work, if you're looking for a job, good time to advertise that fact. And then we'll go back around again, and in the second go around, what I want to do is identify any specific topics that you guys want to cover. Make sure that we get them all on a list so that we can make sure that we get through the day and try to get as many, if not all, the items covered for you. Now, a couple of things in logistics. Deirdre is here from Sun, and she's got the video camera, and she's going to be trying to videotape as much of this as makes clear sense. If you do not want to be videotaped, make sure Deirdre
Tell me now.
Tell her now. Because some people like to remain in the shadows, but
as long as your camera doesn't mind.
Yeah, as long as the camera doesn't break.
No.
One of the ideas about the reason we brought the video camera is not that we're going to go and throw this all up on YouTube, although I guess we supposedly could. But my guess is that maybe we'll edit something down and make a summary at the end of the day. So kind of what I was thinking was two things. One is, at the end of the day, we may come up with some really good ideas out of the workshop, and if so, we'll want to make a short video explaining, those ideas and summarizing them for people who could not attend the conference. The other thing is that it's going to give us an opportunity for you guys to send a message back to the ZFS developers or Sun management, whatever you want to say. Okay, so by all means, this is a good opportunity to take advantage of that feedback to them. Now, you could send an email. Of course, we're JonathanSchwartz@sun.com, right? His email address. Scott Mealy still reads his email as well. But I think it's more powerful if they can put a face to it, and you can say, this makes me mad. Right. Put on your best red, growling face and let them have it. So that's again an opportunity why Deirdre's here to help videotape this. Now, the other thing is, back in the corner we have Cindy Swearingen, and those of you who may follow some of the ZFS stuff, Cindy is the tech writer that writes all the docs. Okay, so this is another excellent example of why I really wanted her at the conference is to get interaction with you guys, since you're consumers of the documentation, or not, as the case may be. To get any kind of feedback, how can we improve the documentation? We've been, Cindy and myself and a couple other people in the community have been trying to keep up with the wiki to keep pertinent, concise information up to date. Sometimes I think we do better than other times on the wiki, but again, this is your opportunity to drive back to us, those things that really we could improve upon.
Speaking of Alex, I don't think there's anything for this session on the Lisa CD, streaming CD, is that right?
That's correct. Yeah. So I don't have anything really prepared, although whatever we come out of this with, or whatever additional documentation you guys think you may want, we'll make publicly available, if it is not already publicly available. We'll make a link and pointers to it. Okay, so with that little introduction, let's go around and introduce people. We'll start right here and just name where you're from, who you work for.
Okay. Tim Sebring. I work for Nationwide Insurance in Columbus, Ohio. I'm an assistant in there. We are soon looking into using ZFS for our root and root mirror. Currently, we've used UFS, ever since.
The dawn of time.
That's right. So we're here to learn more about ZFS and see how we can incorporate that into our environment.
Okay, great.
Randy Rowe from Wells Fargo, based in Des Moines, Iowa. We have other people in my group around the country. We're also interested in the bootability of ZFS right now, looking at possibly replacing Veritas Volume Manager encapsulation for our boot drives and for our data drives. I think we might be able to get a little bit more efficiency out of our storage that way.
Lance Nakata from Stanford Linear Accelerator Center. We're using ZFS mostly on dumpers. We can only use the production version of Solaris, not the open Solaris version, so we haven't tried the bootable root yet, but we are going to look at it now that update 6 is out. So I'm the system administrator for the group.
Hi, my name is Maciej Olchodik, and I work for University of Edinburgh in Scotland. I work for a department called EPCC, which is to do with parallel computing at HPC. I'm a sysadmin there. Last year I've installed the file server for our department, which is like 80 people, based on ZFS, so I deal with ZFS on a daily basis. And I have a few topics that I'll be interested in, but I maybe I'll come back.
I'm Harvey Ditchfield from the University of Bristol in England. We have a 40 terabytes in file store projects, which is mostly Windows at the moment. We're looking at maybe migrating to ZFS, sorry. So I'm in.
Well, same thing for me. I'm here to learn. I'm Jonas Bulthuis from the University of Groningen in the Netherlands. I'm a system administrator and I also hear a lot about the CFS.
I'm Dean Jones. I'm from the University of Arizona Higher Ed Project in Tucson, and we currently use ZFS on ZFS root. We use a lot of local Solaris to get the latest patches. We are working on a big file server project with
Joe Glassman, University of Arizona High Rise. Dean and I are sort of here together to learn lots more about ZFS. I mean, we're basically looking at building a high-performance, high-capacity file server that will basically make our NetApp system obsolete. That's why we're here.
I'm Alan Beatty from Corvallis, Oregon. I'm a system administrator for Peak Internet, a small regional ISP there. We're starting to dip our toes into ZFS, kind of like down to replace an antique NetApp that we've got. I'm using it at home also to kind of play with it. There's been a couple of issues with that I suppose I could relate to.
Hi, I'm Miguel. I work with Ranger Industrial Supplies in Chicago. I'm here to learn about ZFS as far as using it for booting up. We already have ZFS in data region.
My name is Gert Stukwerda from the University of Groningen, a colleague of Jonas. Also working as system administration, and we have a couple of boxes running Solaris ZFS.
My name is Piet Solbers, University of Groningen. We're running those tomorrows for big file systems.
My name is Jim Bugor. I work at Ohio Northern University, and I'm interested also in ZFS booting and maybe learning more about the snapshotting technology.
Lars Egelman, I'm working at the KTH Institute of Technology in Stockholm. We have just a few machines with ZFS. I want to learn more about configuration and maybe backups, and also ZFS on Sparks as with root file system.
Steve Hillman from Vancouver, BC at Simon Fraser University. We've got about a half dozen thumpers that are in process. Some are already in production, some being rolled out. Really interested in stability issues in ZFS if other people had them. Viability of running open Solaris in production to get around some of those issues. And use of iSCII.
Mark Campbell, also from the University of Edinburgh. We deal centrally with sort of larger storage platforms and all the associated services around them. We currently use sort of ZFS a little bit for doing snapshotting for antiquated backups for older systems. We're interested in running up, starting up to do an archive service for offers. There's sort of scalability and cluster make that resilient.
Hans Rankart, Fast Oil in Denmark. We are replacing our main file server, software server, from Solaris 9 to Solaris 10, and I'm mostly interested in the echoes and backing up and snapshotting.
Hi, Grover McKenzie, University of Pennsylvania, Philadelphia. I just bought a couple of thumpers, and I'm looking to find ways to use the thumpers and ZFS along with our standing storage, our NAS heads, and building a digital archive repository.
Bruce Hamilton, I'm with Northrop Grumman in El Segundo, California. We've learned a couple small Zfs file systems, kind of just getting my feet wet.
I'm Tom Baca from National Instruments in Austin, Texas. We have been essentially waiting for bootable ZFS to really get into that. So now we're looking to eagerly looking to do our root disk mirroring and whatnot, and see where ZFS can help us perhaps on our enterprise SAN storage, and who knows, maybe even replacing some of those filers.
Okay, so these are the topics just as you were talking about them that I picked up on. And congratulations, this is about the entire list of topics I could think of too. So there's an awful lot of material to cover here. But before we start maybe looking at specific topics, I'd like to offer that we talk about, or maybe what I could do is go through a presentation that gives a fairly high-level introduction to ZFS. And my concern is that some of you may have never seen it before, or some of you may have seen it before and used it a lot. But I want to make sure that anybody who doesn't know anything about ZFS, at least we come up to speed on the basics of how it works. And the other thing is, occasionally if we get into a conversation, we may refer back to some of the slides in these presentations to understand the point or two. Now there's an awful lot of material out there, and sometimes pictures are better than words. So let me hear it. Do you guys want to go through a short overview, maybe 45 minutes or so, of ZFS, or would that be redundant?
Yes. Yes, please.
Yeah. Okay.
Richard, I'm sorry, but one thing that didn't make it up there that I was thinking about is snapshots and live upgrade, the implications there.
Yes.
maybe illustrating the version.
And we might also want to look at how to convert from just a standalone UFS system, a system that's already installed, and convert that into a bootable ZFS. That kind of goes along with the booting now.
Yeah, well, I have a feeling we're going to spend a fair amount of time on booting.
Yeah.
And we'll touch on some of these issues as well. So that would not surprise me in the least.
While talking about booting, are we going to cover cloning and root?
Yes.
ZFS and upgrading one side.
Yes, so in the live upgrade we'll talk about cloning root, and to some degree the new boot stuff. Now, I know a lot about some of these things, and some of you probably know a lot more about other things than I do, just because of your experiences, or Cindy as well. So it may be that, believe it or not, there may be something we don't know the answer to, we being the collective body. And that's okay, because we'll record those as comments or questions and then find the answers and get that back to you guys. So that's the way I'd like to proceed then with the workshop. So. Can you see that okay? Okay. I'm going to go through this presentation, and some parts I'm going to go through pretty quickly. Some parts I might take a little bit of extra word. And this is a presentation. It's the last word in file systems presentation. It's actually about 2.5 years old. Came out in 2006 when we first started talking about ZFS publicly. The good news is that a lot of the information in this presentation is still very pertinent. And then in later discussions we may get into how some of the effects of new changes will occur and how that works. So let me go through this fairly quickly. Okay, page next. He says confidently. Maybe I'll do it this way. That'll be better for me because then I can see what's coming up to some degree. Persuade itself. Okay. Editorial comment. About once every 25 years, I figure you've got a chance to change your basic root file system. And so the UFS that we've been knowing and loving for a long time in Unix, both really came out of the work done at Berkeley a little bit more than 25 years ago today. Took advantage of the hardware that was available at the time, which was mostly VAXs with hard drives that were small and very unintelligent controllers. Okay, so a lot of the cruft that we have in UFS is because it was designed around how do we get performance out of this thing that was so ancient and old technology, where the OS had an intimate knowledge of exactly where a sector lived on the disk, as far as the head and cylinder and tracks and whatnot. So there's a lot of things in UFS that don't really make any sense in today's modern hardware. The most important of which is that today's disks, a SCSI disk or fiber channel or USB disk, doesn't present to the OS, things like cylinders and tracks and sectors. It presents, here's a big long list of blocks. We start at block 0 and we go to block N. So a lot of the cruft that's in UFS deals with some sort of thinking that it has a knowledge of cylinders. And so you'll see terms like cylinder groups and so forth in UFS terminology. And for those Solaris admins, you'll also will have noticed when you do installations of disks, when you do the installer, it wants things on a cylinder boundary. So when I do a format, you'll wonder why. What does this mean, cylinder? Well, it goes way back to the early 80s, back when the OS actually knew where the cylinder was, and that's just not been our life for a very long time. And so there's a lot of cruft that's built up into the OS that goes back to that old hardware that doesn't make sense on today's hardware. So the other thing that had occurred in the 90s was the concept that came out of Dave Patterson's group at Berkeley for RAID. And so basically what we did in the 90s is we made pseudo disks look like disks and provided the RAID capabilities. So now we're basically faking everything out, right? So we have these multiple layers, and as you probably know, if you've ever system admin a system with software RAID, managing upgrades is very painful. In fact, it used to be we had to unraid the root to then manage the upgrade and then re-raid it. And if you're using SVM, which is built into Solaris, it sort of works halfway. But if you're using like Veritas to manage your root disks, then you had this version thing where the version of Veritas maybe didn't match the version of the OS you were trying to install, and it just became a real bloody mess. And so when they thought about, well, let's revisit this whole thing of disk storage, one thing became very apparent, and that is we need to have a different view of our physical devices. We need to come up to modern times. We need to ditch the notion of cylinders. We need to integrate data protection into the basic things so that things like mirroring a root file system just happens. We don't have to actually think about it too much. And so the concept that evolved out of that is what we call pooled storage. And we'll talk a lot about pools. And for terminology's sake, we should use storage pool. Slang, you'll hear people say Z-pool. Okay, so today I'll probably use half of one, half of the other. And when I write stuff, Cindy yells at me if I do it wrong. So storage pools are then the view then of our traditional disk systems. The other thing that is painful for UFS is file system check. And to give you an idea what file system check does is that as in UFS, while we're writing the allocations, metadata information on the disk, it doesn't do this atomically. It doesn't use a transactional system. It just kind of writes the stuff as we go. And so what happens if you have an unexpected interrupt or reboot, then it has to go back and reconcile, well, is the disk metadata on the disk, is it self-consistent? And if it isn't, then it fixes it. And that's called a file system check program that does that. Interestingly, it's actually sort of separate from the file system itself, file system check. So that's been a problem over the years, although in the past 5 or 6 years, we actually write the metadata into a log. So logging UFS helps eliminate the problem I have to FSCK every reboot, because FSCK on a 1 terabyte file system with thousands of files could take a long time. And in fact, in some of our studies, it could take a week. So you don't want to wait a week for your system to reboot. That's not a good thing. So one of the things that we did was we took advantage of the knowledge of how to do a transactional system. Now, at this point, I asked how many of you have ever managed Oracle or know how Oracle works? Yeah, a couple? Okay. So in the database then there's this redo log. So the performance and work that goes into the redo log is there for when the database has an interruption. Then we come back up and we replay that log to catch up to our current state. And so we have a whole bunch of data that we can asynchronously write out, but we have this log that is very synchronous and transactional. Okay, so ZFS uses the same sort of principle. We have a thing called a transaction group, I think we'll get into a little bit. And we write that out as a log system. Okay. Now, the other thing that's very common in ZFS, and we'll talk about this in many ways today, because it's one of those things that tends to come up and bite you on the one hand, but save you on the other, and that is we have checksums of everything by default. And so we know then if the data on the disk is wrong, or let me rephrase that, we know if the data we read isn't correct. So we'll talk a little bit about how that works as well. So we wrapped all that up in this idea of simple administration. You guys will tell me if we're really simple or not. That's a good item of feedback as well today.
Checksums are built in, does that mean dedupe to be coded easily?
Excellent question. Let me put that on the list of things. Because dedupe. Okay, I'm not going to talk about this slide really. So, this is sort of the mantra when they first came out with ZFS is, we're going to end the suffering here. And I think the most important takeaway here is really we're going to blow away these assumptions, right? The 20 years assumptions about cylinders and disks and inner cylinders being faster than outer cylinders, which didn't exist back then, or even the fact that we have solid-state devices now gaining traction rather rapidly. So we wanted to redesign this thing. So we talked a little bit about why volumes exist. I don't want to dwell on this at all, other than to say, from an architectural perspective, this model here, where I have a file system on top of a disk, there's assumptions that are made in the file system about how it's going to work, and then there's assumptions that the disk makes about how its interface occurs. So we have an interface here, and typically it's a SCSI level interface. Even if you're running Fibre Channel, we actually run SCSI protocol over Fibre Channel, right? So typically there's an interface here which is industry standard and fairly difficult to change, shall I say. And so when we introduce volumes, we basically move that interface up here. So we have this interface from the file system perspective. The volume looks like a disk. Okay. We still have the problem that I can't really change the basis of that API layer. But then I have all this software running down here, which I can deal with. But so basically, this volume software is busy making these disks with their protocol interface look like a disk to a higher level of protocol interface. So that's actually somewhat troublesome. And how do we want to better integrate the file system to the underlying device storage? So in the pooled storage abstraction, we actually are taking an approach here that looks like memory. Okay, and I usually try to tell people, if you think of this as memory allocation, then you'll actually get a lot of insight to how things work. So, for example, on your main memory system, most of you have laptops. Most of you on this laptops have one DIMM or SODIMM of memory, right? And on a big server, though, I may have hundreds of DIMMs of memory. And on our big servers where I can dynamically add and remove memory, right? Now I have this issue of I've got memory allocated on a DIMM, and I'm going to remove it from the system, so I've got to take that memory and move it to another DIMM, and then release that memory. Or if I add memory into a system, then now I have more memory that I can use on my system that I can allocate. Okay, so it turns out that that approach works very well for disks as well. I can add disks, I can remove disks, and we'll get into some of the nuances with that with Zfs. But I can add disks, I can remove disks, and really what I'm doing in the file system is I'm allocating memory onto the disks. Okay, so if you can take away that little bit of understanding, then some of the things you may see in Zfs will actually make more sense. So here then is sort of a brief approach of how that works. We have a file system volume. We'll actually talk about some of these things at periodic times. ZPL is the Zfs Posix Layer. So those of you who use traditional file systems as traditional file systems, you know, like ls, directory, maker, create a file and whatnot, that's all done at the Posix layer. And since it is an industry standard, POSIX standard, there's also constraints about how that operates that will come up and irritate you occasionally. The ZPL layer is a layer and can be replaced. Okay, so if someone comes up with a new way they want to do a file system or a way they wish to layer upon the ZFS underpinnings, it's certainly possible and plausible to do that. It's open source and the interface is well defined and you can leverage it. So one of the things that a group is working on is how do we take Lustre, which is a distributed file system, and leverage ZFS backend. And where they're looking at doing that is, rather than having a ZPL layer up here, then they'll add a Lustre layer. So if you follow the workings of the Lustre group, you'll see that's where they're active. So basically, some of the Lustre stuff will appear up here, and then we'll still use the lower layers of ZFS in the backend store. So the DMU is the data management unit layer, and that's where your RAID occurs. Okay, so most of the functions, in my opinion, is really how the DMU works and how your RAID is done back there, as well as the transaction groups commits are done there as well. And then the storage pool allocator, we won't really talk about that today. Probably, maybe we'll talk about it if we talk about performance issues. But so that's sort of the three major layers that we'll deal with in ZFS. Yeah, here's an example then of other things that can in fact occur. So the Lustre people, for example, are going to leverage the DMU. Okay. Another thing we'll talk about today, though indirectly, I probably won't actually spend much time on, is the Zfs Volume Emulator. In this case, rather than presenting you a file system with POSIX rules, we give you what looks like to your application a raw device. And that rides again above the DMU. So when you do iSCSI in particular, or swap dump, then that'll be over the volume, or ZVol. And also here it's called ZVols. That's what we mean by the volume emulator. So it looks like just a raw disk. Okay. The other feature that's prevalent and leads to some interesting discussions on ZFS is the copy on write nature of the system. So the idea from a reliability perspective is if we can avoid overwriting data, then we can make it more reliable because I'm never destroying data, right? And so we do implement copy on write semantics. So the way it works is the storage space allocator keeps trees which contain the allocation of space. Now we use that space for both data and metadata. So from the allocation perspective, it really doesn't matter if we're talking about data or metadata. We'll allocate that out. So let's say we have an existing tree, and then we want to update some blocks. Rather than overwriting the existing blocks, we'll allocate new blocks. And then when we do that, we have to update the pointers back in the metadata. So we have these two new active blocks because we wrote some data. Now we have to go back up and traverse back up the tree and update all the metadata, which is also done copy on write. Okay, so basically we do that all the way until we get back up to the top. When we get up to the top, we have a thing called an Uber block. And especially when we talk about troubleshooting, you'll hear us talk about Uber blocks. The Uber blocks have to be in a specific known location. Otherwise you can't start, right? So since they are in a specific known location, we have this issue in that I just told you that we allocate new space for everything and we don't overwrite data, but then we have this Uber block thing that has to be in a specific location. And so rather than overwriting it, the Uber block is implemented as a circular queue. Okay, so the Uber block does have 128 slots, if you will, that's operated in a circular queue. And that, again, if we dive into troubleshooting later, that's an important aspect to remember. Okay, so that's how the copy on write works. Now, the cool thing about this is if I want to take a snapshot, I want a point in time view of that file system, then all I have to do is not free the old blocks. Right? So I copy new blocks when I write, but then the old blocks are still there because I haven't overwritten them. And the question then becomes, do I return those blocks to the free pool or not? And if you don't, we call that a snapshot. If you return them to the free pool, then it's not a snapshot, right? So basically what that allows us to do then is come in periodically, or whenever we want actually, and just say, we'll snapshot this, and then it will not return those blocks to the free pool. Has implications for you, especially those in academia who have very little control over what your users write. Managing snapshots and wild users is sort of an issue. Also, how do we understand how to account for that space is a challenge as well. Okay, so anyway, that's how copy on write works. That's why snapshots are available and free. This is basically saying the same thing. I don't think we're going to get too much into troubleshooting today, but if we do, then I'll refer back to this sort of a slide. And the important thing to keep notice is that there's a monotonically increasing counter that counts the transaction group. Okay, so and when you look at some of the metadata with some of the tools like ZDB, you'll see a transaction group number, and you'll see over time that number just increases. It's an unsigned 64-bit thing, and it increases monotonically. That's how we know the age of data in the overall scheme of things. So that's how we can keep track of what is where. And again, that becomes an issue. It's a detail about how we implemented this thing, but it also becomes an issue in troubleshooting. You may want to deal with that. Okay. This slide, at this point, I usually pick on UFS. UFS was designed in the times when 40 megabyte hard drive was 14 inches in diameter, and the spin up of it would shake the rack, kind of a thing. And that's when UFS, that's the environment was done. They couldn't dream, or they could dream, but they really had no way of knowing that we would have 1.5 terabyte drives in 3.25 inch form factor today, right? And so the drive capacity limit for UFS is really 1 terabyte. Now, we hacked in some stuff to allow it to go to 16 terabytes in theory, but there's trade-offs to be made there. Most importantly, we had to make some trade-offs in how you're going to FSTK this thing in less than a week. Okay, so UFS, to kind of put it bluntly, out of capacity, it doesn't work well on big disks, and now everybody has terabyte disks, right? So there was no doubt we had to do something different. Another important thing from a RAS perspective, and if you guys don't know the acronym RAS, I'll use it a lot. It's reliability, availability, serviceability, and it's really the work I do every day. And RAS it was hard enough to get things working in the early 80s at all, right? And so you were real happy, hey, I got it to work. But they didn't put in to those systems any real fault recovery. Okay, so what happens when your 14-inch disk drive lost a few blocks? Well, you lost data, and darn it, you got it back from tape, assuming your tape copy was good. But for the most part, you really didn't know, right? The buses were parity protected at best. In fact, some of the early buses in the PC space didn't have even parity protection, so you really didn't know if your data was bad or not. So we actually sense, and we actually can measure quite a bit of data loss in systems. Now, that still occurs today, although the systems are much better than they were then. There's very sophisticated on disk drives today. There's very sophisticated error checking that takes place, but there's still cases where you're going to lose blocks, or the terminology I'll use is unrecoverable reads. Right, so I wrote data to that disk, and I go to read it, and the disk says, I couldn't recover it. Sorry. Here's a bunch of zeros. Hope that makes you happy. And so the assumption then in ZFS was completely opposite. The assumption in ZFS is that your hardware is broken, it's going to lie to you. Okay, now let's deal with it. And so that different approach leads to a lot of the behind-the-scenes fault protection and recovery mechanisms that are in ZFS, and we leverage checksums to make that occur. Okay. So what we're seeing then is a rapid increase in error rates. Now, why is that? The main thing, the reason that occurs is because the systems today can actually tolerate a lot more errors than ever before. So back in the old days, on an SMD disks, we might have one spare sector per cylinder or per track. And the OS actually had to manage these sorts of things. Well, today on your disks, you buy, go down to Fry's and buy a 1 terabyte disk, and all that is behind the scenes taken care of you. How many spare cylinders are there, or spare sectors? I don't know, and I really don't care. So all that, what that means then is that the disk vendor can give you a device that can actually tolerate a lot more errors than you would ever think were existent there, but most of the time you never notice. Okay? And so the way we do it in ZFS, we really want to take that up another level and say, okay, Mr. Application, there's going to be errors in the system, and I'm going to try my very best to hide them from you. Okay? CERN did a study of this, There's actually a newer study that came out in January of this year, study done with Metadata and, if I'm not mistaken, Carnegie Mellon, on soft error rates on disk drives, and they studied a substantial population of these and measured that. And so again, basically it gets into that situation where NetApp has a checksum in their file system as well, and they can detect these, the data comes back from the disk and you think it's right, and the checksum says, no, it's not right. And so they did a good study on measuring that. It was done at the FAST conference in January. Excellent paper, I highly recommend it. But basically what they were finding is that there's a lot more silent errors or checksum errors out there than maybe we ever thought. And so to build a modern system, we have to deal with that. So we do checksums. And the important thing of the checksum in the ZFS environment is that the actual checksum is not stored with the data. The actual checksum is stored, to one level above the data, the metadata. And then this metadata is then checksummed, and its checksum is stored in its metadata, one level up. So basically, there's always somebody validating the checksum for somebody underneath it. Okay, and from a consistency perspective, that's a very clean design. So anyway, there's a whole bunch of bad things that can happen that these checksums will detect. And I'll use a quick example here then of why that's important. And I've been many times bitten by this particular problem. So I have scars. I hope none of you have scars, but I have scars. And that is, in a traditional logical volume manager like SVM, it's going to write disk or data to the disks. It doesn't do a checksum. So the only way that SVM knows that if I'm reading from a mirror, the only way SVM knows if I had a real problem is if the disk says, oh, by the way, I detected this error. Or if the disk doesn't respond, for example. So the disk could return back data without an error code, which, believe it or not, does happen. And the mirroring software will say, well, the disk gave me the data, therefore I believe the disk, and therefore I want to send that right back up to the application. So obviously the application shouldn't be very happy about that. So in ZFS, what happens is we read the data from the disk, we calculate the checksum. Checksum may or may not match. If the checksum doesn't match, then we'll go read from the other side of the mirror. Okay. So not only are we detecting the disk faults that are reported by the disk, but we're also checksumming the data and validating the checksum. And if the checksum doesn't match, then we'll try to recover the data. Okay. Now this will happen behind the scenes for you, but the idea is that the application will get the correct data. Now, there's an important assumption here that you will revisit many times as you design these systems, and that is ZFS in this case is managing the data redundancy. Okay. For people who really like to use hardware RAID controllers, they will make the argument that I don't want ZFS to manage the data redundancy. I want the hardware RAID controller to manage the data redundancy. Okay? Perfectly valid argument. Okay? The trick is that if ZFS is not managing the data redundancy, then ZFS can't repair the data if it's broken. Right? Makes sense. So just keep in mind that's the difference then of where you assign in your design the data redundancy to occur and things to be fixed. This is a very common trade-off we see quite often.
Is there any metric for that trade-off?
No. Okay. Usually the metric comes down to dollars. It comes down to, I just spent $1 bazillion on this EMC box or Hitachi box, and I want to get every last penny of value out of the box, and so that's when they'll make that trade-off. Okay.
The other metric is some really sad stories.
Or really sad stories. Yeah, that's true. That's
How about a performance metric then? I mean, what's the difference between ZFS and some relative number?
relative numbers. Typically, if you have a hardware RAID controller and you're doing like a RAID 5, for most workloads it will outperform ZFS with doing RAID Z with JBoss. Not always, but there are optimizations because the RAID controller can utilize non-volatile write cache. So we see it more on the right side of the equation. But there's also some issues with the way checksums work in ZFS, so that impacts the read side of the RAID Z equation. Now for mirroring, you're pretty much going to be the optimum speed in most all cases. Typically when we start worrying about the performance differences, then really the trade-off becomes, do I mirror, which gives me the best performance, best redundancy typically, but not the best price per gigabyte, versus something like a RAID Z, RAID 5, versus nothing. Now hopefully you'll never leave here thinking nothing. Right? Or as I like to say, friends don't let friends do RAID 0. So you'll see those trade-offs. So I tend to try to remain flexible, although I'm biased against RAID 5. Sorry. I'm not going to talk too much about the write hole, but I will talk a little bit about this slide. You don't see this slide too often approached. Now, people often ask me, well, why do you call it RAID Z instead of RAID 5? Or why do you call it dynamic striping rather than RAID 0? And the reason is that RAID 5 and RAID 0 have well-defined definitions in the storage industry. And dynamic striping and RAID Z do something different. So this is a pretty good example then of how a RAID Z can work in that it's dynamic. So in a RAID 5 world, you'll have like a 4+1, yeah, that's what I have here. So in a RAID 5 world, we'll have 4 devices, A, B, C, and D, E and E, and then we'll have the data spread across them with a parity. Now in the RAID 5 definition, those are fixed. You'll hear people talk about interlacing or stepping or something to describe the relationship between the blocks and the parity spread across the devices. In RAID Z, if I don't have enough data to write a full stripe in a given transaction group, then I don't have to use the whole stripe. I'll use a subsection of that. An example appears in red where we have just 2 devices being written, 1 parity, 1 data. Okay, so in theory, for certain workloads, we're going to see the case where I won't calculate a full stripe-wide write for RAID Z. And so it's somewhat dynamic in that regard. Now, in all cases, you're going to have data and parity. The question is then how many, how wide is that full? Or how wide is that data spread? So that is a very subtle difference. I will say, though, in practice, we don't see this very often. In practice, we tend to see the writes come through pretty much fully wide, especially if you're writing anything sizably large, like a large file. And it will be all the way wide. Okay, so this brings up a practical question for you, and that is, okay, well, I know if I'm doing RAID 5 and I've got 4 disks plus a parity disk, then my available space is 4 times to this size. Okay. What RAID Z says is this: it says, well, maybe not. So how much space do I have available in a RAID Z volume? And the answer is it depends on how you use it. Okay, so we'll circle around this issue of how much space is available and how much space am I using several times during the day. The best thing I could tell you right now is, okay, it's dynamic. There's lots of things at play here. So just keep that in mind. Next. A couple of things about how do we resilver. Because there's a couple of twists here that are going to impact you, or you may see impaction as far as the efficiency of resilvering data, recovering data, or the efficiency of creating a snapshot, or in fact the time it takes to do these sorts of activities. And that is when we do you remember I had the slide that had the transaction group numbers? So I had the metadata, I had transaction group 37, 38, or what have you. When we resilver, we actually follow that same pathway. So we actually go through the transaction groups in order to resilver data. Okay. The reason we do that is because that data then is consistent to the transaction group that's committed. Again, it's transactional oriented. So if we just did a blind DD, or a blind copy from block 0 to block N of the device, and our data is spread out all over the device, then we actually lose that connection between, is the data on that block of disk actually what I need it to be, because it's just done sequentially. Now, when you do it sequentially, it goes very fast because I can just crank up, it's a sequential read, it's a sequential write. I can go at immediate bandwidth, basically. In ZFS, when we resilver, we do it by transaction group. We start the lowest number of transaction group and work our way forward. So what that means is you're going to see a lot more seeks as we go around and collect data from the various transaction groups to do the resilver. Okay. And that, again, we'll talk about that effect when we talk also about snapshots. So there's an interesting effect then, though, if I have a simple mirror case, and let's say I have 2 disks that are mirrored, and I'm in the process of resilvering the one disk, and my original disk craps out. Okay. Then what I have on my partially resilvered disk is still consistent file system. It's just at some point in time prior to today. Okay. So that has some interesting implications about things that can happen. Clever to think about when you're thinking about troubleshooting as well. And that's what we talk about here. We do top-down resilvering. The other thing is, since we're only copying our data, we don't have to copy data that's not, or blocks on the disk that are not assigned. So now the resilvering time is now a function of how your data is spatially located with all the metadata, but it's also a question of how much data am I using, or how much space on the disk am I actually using. It's not dependent on the size of the device. Okay, so again, they're a little different, a little bit different there. Blow through that. And I want to talk about, for just a moment, about ditto blocks. We use the term ditto blocks to describe a technique whereby we make copies of data at the ZPL layer. Okay, now remember, our RAID 0 or mirroring or RAID Z is done at the DMU layer, and above that we have the ZPL layer. And I can make copies of data there. It's called the copies parameter, so you'll often hear us talk about copies. So we have copies. Copies are ditto blocks. So the first thing we do is, in all cases, we're going to copy metadata. So for all the metadata that we talk about, losing metadata is a really bad thing. So the decision was to always have at least one redundant copy of metadata. Okay. The good news is that metadata is typically not very physically large, and also metadata is highly compressible, so we also compress it. So metadata is compressed and copied. Now then, with the copies parameter, you can set on a per file system basis what your copies should be. And the example I use is, my wife is a writer and she takes pictures and does this sort of stuff for a living. And also she has pictures of her fondest memories and stuff. And she would be really upset if she lost a picture, right? So, for her pictures directory or pictures file system on her desktop, I've got the copies parameter set to 2. Okay. Because I know who's going to get you in that case. For the OS though, right, OS files are mostly read-only, and if I lose a file, I can restore it off media. So for OS files, I don't care, I'll leave copies the default of 1. So what it allows you to do with copies is, over and beyond the data protection done at mirroring or RAID Z, I can also have additional data protection on a per file system basis. So I can set a policy then, this file system contains very important data, I want extra protection on it. Okay, so that's one of the things that comes about because of ditto blocks.
Is it for file system or for directory?
For file system. Okay. Now naturally, since we have checksums and we have all this stuff running around, it makes sense to have something that goes around periodically and checks your checksums to make sure your data is okay and recovers when it can. That's called scrubbing. There's a zpool scrub command you can run that will kick this off. Some people like to do this in cron tab. Some people with very important data do it more frequently. Some people aren't so worried about their data, do it less frequently. Some people don't know about it and do it never. My suggestion to you would be, for the most cases, you will want to try to do a scrub at least once a year. Okay, you might do it once a month or so. Doing it every day is a bit of overkill for the vast majority of cases. So, so scrubbing is one of those things that